Okay, let's have a look at this past exam question. So we've got a function here that we're considering log of sec of x. Now what sec of x is, by the way, is 1 over cos of x. And it has a derivative sec of x tan of x, as you can see if you differentiate this using the quotient rule and do some messing around. This derivative, I would probably, there's at the back of this manual, is there an exam paper? I don't know, I'd probably have to give you the derivative anyway in any assessment, okay? And we're also going to need the chain rule, which we saw a little bit previously, but let's write it again. So it's going to be a situation where we have an outside function and an inside function. How do we differentiate it? So it's basically x is sent to I of x, which is sent to O, like so. This, you see, x is sent to sec of x, and then the log is taken of sec of it. So it's two functions applied twice. That's a composition, and to differentiate it, you need the chain rule. It looks like outside inside. So the chain rule says you differentiate the outside function, evaluate it at the inside function, and then times the derivative of what's inside. Okay, so we have to show that the second derivative of this is sec squared. So let's do the first derivative. So f dashed of x, let's use the chain rule. So the outside function here is log of x. So I ask you, what is the derivative of log of x? And the derivative of log of x in a table or whatever is 1. I might be able to send you tables as well. So 1 over x. The chain rule says you evaluate the inside. So instead of 1 over x, evaluate at x equal to the inside, which is sec of x, times the derivative of what's inside, and the derivative of sec is sec by tan. And now sec of x divided by sec of x is 1. 1 by tan of x is tan of x. So that's the first derivative. And to find the second derivative, we differentiate again, and the derivative of tan of x in the tables, it's sec of squared, so we're done. Okay, so next thing is find the first two non-zero terms of the Mclaren series of f of x. So this is our formula that we use, and that pattern keeps on going. So we're going to calculate these numbers, f of 0, f dashed of 0, etc. So we're going to calculate these first three numbers. The value of the function log of sec of x at 0, the value of the derivative at 0, that's tan evaluated at 0, and also we're going to calculate the second derivative, which is sec squared, evaluate that at 0, and then divide it by 2. Okay, so let's calculate those on the next page. So f of 0. So this is log of sec of 0. Now sec of x is 1 over cos of x, so it's not in the calculator. Log of 1 over cos of 0. Appreciate the writing is a little bit small here, so hopefully you can hear what I'm writing. And cos of 0 is 1, and 1 over 1 is 1, so you get log of 1, and you may or may not remember this from chapter 1, probably not. Log of 1 is equal to 0. So this first term here is equal to 0. That's no good to us. Now let's look at the derivative, because the question is looking for first two non-zeros. That's first term, second term, fourth term. First, second, third, fourth. But we're looking for two non-zeros. So we'll look at f dashed of 0. The derivative was tan of x. So this would be tan of 0. And tan of 0 is sine of 0 over cos of 0. And sine of 0 is 0. So it's 0 over 1, which is equal to 0. So that means that the second term is also equal to 0. Now we'll go on to the third term and we'll look at the second derivative. And we know that second derivative is sec squared. Okay, now what does sec squared mean? Well, the squaring there means sec of 0 all squared. Sec multiplied by itself, or sec of 0 squared. That's what we're dealing with here. And sec of 0 is 1 over cos of 0. And cos of 0 is 1. 1 over 1 is equal to 1. 1 squared is equal to 1. Okay, so this term here, we have something. We have the second derivative evaluated at 0 is 1. Divided by 2 factorial, which is 2 by 1, which is 2. So this is a half x squared. Now let's look at this term. Okay, this means because we need to get first two non-zero. We've got 0, 0, non-zero. We need one more non-zero. So we also need to look at the third derivative evaluated at 0. So we need to differentiate sec squared. Where's sec squared coming from? Well, the second derivative is sec squared. So to get the third derivative, I must differentiate sec squared. So the third derivative is the derivative of sec squared. Now the way I'm going to think about sec squared, there's two options actually. You could think of it as sec of x times sec of x and use a product rule. That's fine. I'm going to use the chain rule, which is sec of x all squared. So with sec of x all squared, the outside function is x squared. And the chain rule says differentiate the outside function. What's the derivative of x squared? It's 2x. The chain rule says evaluate at the inside, which is sec of x. And then we must multiply by the derivative of what's inside. And the derivative of sec is sec by tan. I'm going to tidy this up and then evaluate it at 0, because this is the third derivative. I need to evaluate it at 0. So tidy it up for, well, we'll need it in a minute. So 2 sec by sec is another sec squared by tan of x, and let's evaluate that at x equal to 0. So evaluate that at x equal to 0. And what happens is, we've already seen sec squared of 0 is 1. So I got 2 times 1, and tan of 0 is equal to 0. So this term also gives us a 0. So we have to go to the next one. Now the pattern keeps going. So the next one is the fourth derivative, which I might write using kind of Roman numerals. Evaluated at 0 over 4 factorial times x to the 4. And in theory, you might have to keep on going. Right, so we need to find the fourth derivative evaluated at 0. So we must differentiate this again. Now what I'm going to use to differentiate this, because it's things multiplied together, I'm going to use the product rule. Well, I have to use the product rule. So the fourth derivative, I'll go back to 1, 2, 3, 4 of x. And what does the product rule say? The product rule says it's the first thing, 2 sec squared x, times the derivative of the second thing, and the derivative of tan is sec squared, plus the second thing, which is tan of x, times the derivative of the first thing, which is 2 sec squared x. So that's the fourth derivative, and I need to evaluate this at x equal to 0. And so I end up with 2 times sec squared evaluated 0. Sec squared of 0 is 1. So you get 1 times 1 plus tan of 0 is 0. So it doesn't actually matter what actually comes after that, because it's 0 times. So it's 2 by 1 is equal to 2. So what we get down here is this bit is 2 over 4 factorial. Now 4 factorial is 4 by 3 by 2 by 1, which is 24. So 2 over 24, x to the 4. And they're the first two non-zero terms. So log of sec of x is approximately 0 plus 0 x, which is just 0, plus 1 over 2 factorial x squared. So that 1 is coming from up here. 0 is coming from here, and the 2 is coming from here. So you end up eventually with log of sec of x is approximately equal to a half x squared plus 12 to x to the 4. I will say, in terms of the differentiation, that's pushing you. Look, we'll see what the assignment comes up with. So this is a good approximation for x approximately 0, because actually what happens is, if you look at the higher powers, so what I mean by the higher powers, I mean multiples of x to the 5. And that's what we're looking at after this, multiples of x to the 5. If you're close to 0, and you do a small number to the power of 5 or a small number to the power of 6, they're very, very small. So basically, if you keep on going, so I'll show you what I mean down here. So log of sec of x, and this time we'll go equals half x squared plus 1/12 x to the 4, and then everything else is like you got a multiple of x to the 5 plus a multiple of x to the 6, and I'm just going to use that order notation, multiples of x to the 7. So for example, x to the 8 is a multiple of that. So if x is small, we'll take this bit. So if x is small, sorry about the dogs, nothing I can do about that, then these are small as well. So for example, take x equal to 0.1 and look at, say, 0.1 to the power of 6, it's a small number. Okay, so this is actually a good approximation, close to 0. And indeed, if we look at the story here, so the inside curve is log of sec of x, and the outside curve is the degree 4 polynomial, and it's a good approximation between these two. I'm not sure what happens outside here. It might be the case that actually, so like this is the x equal to 0 Mclaren series, and maybe it's only really valid for between -1 and 1, so that no matter what you add on here, you're not going to get a good approximations here. And maybe that's true, and there's various different reasons to believe that. Basically, if sec gets it's kind of hard to think now, but I think, yeah, if so I think near pi over 2, I'll just show you an issue. So at x equals pi over 2, which is approximately 1.57, which we might be able to see on this 2/4. Yeah, so yeah, coming up to here, what happens is sec of x, which is equal to 1 over cos of x, and what happens is cos of pi over 2 is 0, so this is like 1 over very, very small, and that goes very, very big. So you get sec of x gets really, really big here, and even if you take log of a very, very big number, it gets very, very big. So this goes to infinity, and you can't approximate that probably very well. So it's probably just valid between these two, or maybe even out to plus or minus pi over 2. That's kind of beyond what we're looking at. Really look in between those two. Sure, there's nothing between them. That's what we're looking at. Okay, we'll do another example here. Find all terms up to x cubed in the Mclaren series of this. So we'll write down our little formula for the Mclaren series. So it says that f of x, now if we use up to x cubed, we won't say equals, because we're not using the x to the 4 on, we'll just do approximately. So it'll be f of 0 plus f dashed of 0 times x plus f double dashed of 0 over 2 factorial times x squared plus f treble dash 0 over 3 factorial times x cubed. Now the pattern does actually keep going, because this, you could see this as x to the 1, which is just x, over 1 factorial, which is just 1, and this is x to the 0, which is just 1 over 0 factorial, which you think might be 0, but actually it's equal to 1. Right. So off we go. We need to calculate for this function, we need to calculate these numbers. So first of all, let's run with f of 0. That's probably the easiest one. So this is equal to log of 1 plus 0, which is log of 1, which is equal to 0. So this first term is 0. Let's go and calculate the first derivative. So we've got an outside function of log, inside function of 1 plus x. So the chain rule says you differentiate the outside function, the log of x. What's the derivative of log of x? 1 over x. The chain rule says evaluate at the inside. The inside is 1 plus x. times the derivative of what's inside, and the derivative of 1 plus x is 0 plus 1. And 0 plus 1 is just 1, so you have 1 times 1 times 1 over 1 plus x, which is 1 over 1 plus x. And now we're going to evaluate this at x equals 0, and we will get 1 over 1 plus 0, which is 1 over 1, which is equal to 1. Okay. Now let's go for the second derivative. Now you've got two options for differentiating the first derivative. I'll just show you what they are up here. So kind of one way of doing it is you can see that this is a u and a v situation, and you can go off and use the quotient rule if you want. Alternatively, it's divided by 1 plus x once, and division is a negative power. And then you can use the chain rule. This is what I would recommend, and this is what I'm going to do. Okay, so actually this probably would have been a good question for the assignment. Anyway, okay, so the second derivative here is differentiate 1 over 1 plus x. So I'm going to differentiate 1 plus x to the power of minus 1. Now here the outside function is x to the minus 1. And what's the derivative of x to the minus 1? Well, how do you differentiate a power? You multiply by the power and then reduce the power by 1. So you go from minus 1 down to minus 2. The chain rule says evaluate at the inside, and then the chain rule says multiply by the derivative of what's inside. Now this inside is remaining as 1 plus x, and we know that the derivative of 1 plus x is just 1. So I get this. I might just tidy this up for differentiating next time. So minus 1 by 1 is just minus 1. So minus 1 times this, I just have minus 1 plus x to the minus 2. Just tidy it up before I differentiate it next time. Then evaluate this at x equals 0. And I get minus 1 plus 0 to the minus 2. And that ultimately at the end of the day, this is 1 plus 0 is 1 to the minus 2. 1 to the power of anything gives you 1. So I have minus 1. And now I just have to go at the third derivative. So I need to differentiate this yoke. I'm going to fix the constant. The minus there is like a minus 1 multiplying. That's a constant. I can fix that. Or maybe we'll do it a bit more explicitly. And now we want to differentiate 1 plus x to the minus 2. So the outside function is x to the minus 2. Chain rule says differentiate the outside function, x to the minus 2, multiply by the power, reduce the power by 1. That's minus 2x to the minus 3. Evaluate it at the inside, times the derivative of what's inside, which is just 1. Okay, and I want to evaluate this at x equals 0. And I would get minus 1 times minus 2 times, now this will be 1 plus, that's just 1 to the power of minus 3, that's 1, times 1. So minus 1 by minus 2 is 2, by 1 plus 2. And so we're done here. We're going to use this formula. Log of 1 plus x is approximately equal to f of 0, which is just 0, plus f dashed of 0, which is 1, times x, plus f double dashed of 0, which is minus 1, over 2 factorial times x squared, plus the third derivative evaluated 0 is plus 2 over 3 factorial times x cubed. And it'd be nice to tidy this up for a final answer. Log of 1 plus x is approximately equal to this, which is equal to this. So log of 1 plus x is approximately equal to this. 0 I can leave out. 1 by x is just x. This is 2 factorial is 2 by 1, which is 2. So this is plus minus, which is minus. Yeah, let's leave it 1 over half x squared. And then 2 over 3 factorial. 3 factorial is 3 by 2 by 1. So it's 2 over 6, which is 1/3. X to 3. And you can guess how it keeps going. And that's how a calculator calculates logs near 1. Okay, this is valid, by the way. So in roughly, it's for x close to 0, and in fact you can show that it's only for x between minus 1 and 1. A good question is to ask yourself, it might actually work at 1. it might work at 1. Good question to ask yourself is what happens at -1 into this format? Okay, so hence find correct 4 significant figures an approximation to this. So an approximation to log of 1.1, and here I kind of helped. The x is 0.1. So log of 1.1 is approximately, use this thing, the x is 0.1, 0.1 minus a half 0.1 squared plus a third 0.1 cubed. And what does this come out as? Now because of the third, we'll only be able to, it's 4 significant figures. Okay, so I get 0.1 minus 1 half 0.1 squared plus 1/3 by 0.1 cubed. And it's coming out like this. We're just doing 4 significant figures. 0.95. Now see that dot? You might have pressed this again. 1, 2, 3, 4, 9533. Okay. Now how does that compare with what the calculator says? 95. It's not bad. It's correct to three significant figures. Well, excuse me, getting a bit tired there. 0.09533. It's correct to 3 significant figures, 4 decimal places. Now, just a small comment: if you're asked to find the percentage error in approximation of some quantity, note that the percentage error is given by the error over the true value. So be careful. It's error over true, not error over approximation. So the percentage error here, you do the error, the difference between the approximation and log of 1.1, and even that, by the way, is only according to the calculator, is approximately equal to this, and you multiply by 100%, it's 0.02%. So it's a very, very good approximation, but it's only valid for x close to 0, and the further away from 0 you get, the less valid it is. Now the next question, I think we've only one more short lecture. I'm going to finish here.